Hello, everybody. My name is John Wilkes. I have the privilege of being the Chief Executive of the Institute of Health and Social Care Management. And today, this is a power hour to end all power hours. I'm so thrilled to welcome someone who really brought a subject alive for me personally earlier this year, Sarion Bowers, who is a member of the Wellcome Sanger Institute and took me on a guided tour of the Institute to show me all of the work in respect of genomics that they've done. She showed me the code books and so on, which is just an extraordinary thing to see. It wouldn't surprise me one jot if she's got some images to share with you as we go through this. But Sarion, I am so grateful to you for coming along and agreeing to just talk about the work of the Wellcome Sanger Institute for our members. And without further ado, I'm going to hand straight over to you, if I may.
Thank you, John. I thank you for inviting me and thank you for that very warm welcome. Unfortunately, I don't have a picture of the books, but I suspect you can Google it actually, that if you have a look, because we do have a printout of the human genome, and I can't remember exactly how many books, but it's roughly 50 large books, all in about 4-point font. So that's how many books
I'll find the photo and pop it in the chat. How about that?
There you go. So as John mentioned, I am head of policy at the Wellcome Sanger Institute, which is probably an institute you have never heard of, and yet I suspect many of you will have actually heard of some of our projects and some of our work. So we are, my slide, oh, there we go. So we are an institute based just outside of Cambridge, and we use information from genome sequences to understand biology and improve health. And we do this, we have a strategic profile that is really around identifying the very frontiers of biology. So we try and really be working at the very bleeding edge of research. And we use genomics and the implementation of genomic technologies to do this. Our projects are all massive scale, so it is a little bit go big or go home around Sanger. Many of our projects are actually intended to last 10 or 20 years, which we are very lucky with our funding that we're able to do this. There's very much an element of we try and conduct research that can't easily be done anywhere else. And if it can be done somewhere else, then probably it should be done somewhere else. We are expert in aggregating, analysing and interpreting large quantities of genomic data. And we work very much in collaboration. So we initiate and lead national and international collaborative initiatives, some of which I'll talk about. And we do this in order to be able to kind of get that kind of scale and reach that you really can't do as an organisation on your own, and sometimes even as a country on your own. And it's also really important to us that we incubate the next generation of scientists and clinicians in genome research. And so we do this obviously through a lot of training, but we also are very thoughtful about how we do our research as well to try and ensure impact. And actually the picture on this slide is of our NovaSeq sequencing machines. So we have probably one of the largest sequencing fleets in the world, but our NovaSeq fleet is for short read sequencing. So this allows us to do very, very high throughput technologies. And actually today I just saw our new NovaSeq machine, which is basically going to allow us to scale up again from where we're at. And so these are really the sort of cutting edge machines that allow us to produce the equivalent of about 3 human genomes per minute. So we are a research organisation, we are a discovery research organisation, not for profit. So we have a roughly £120 million a year budget, which is obviously sizable. 80% of that comes from Wellcome. For a long time, this was the largest grant in the world. I think there are a few bigger ones now, but not many. And about 20% of our funding comes from other funding sources, which I think some of these will recognise, like Cancer Research UK, UKRI, NIHR, but also the Chan-Zuckerberg Initiative in the US and the Bill and Melinda Gates Foundation. And these very much speak to our strategic priorities. In many ways, we look a bit like an academic department in a university. We are led by, our science is led by our faculty, and so they are our research group leaders. We have about 30, we're actually now up to about 35 faculty, and within those teams, they will have PhD students who are all students at the University of Cambridge, and we have postdoctoral research fellows. But where we then become quite different is we have around 300 members of staff working in our scientific operations teams, and these are our high throughput pipelines. So they're the people running those NovaSeq machines, but also PacBio, Oxford Nanopore Technologies. They are the ones scaling up and really pushing through our massive data production. We also have a number of people within the scientific programs who are supporting those researchers. So there's another 330 people there. And then we have our what we call management operations, but these are effectively corporate services, so HR, finance, that kind of thing. And Wellcome is really committed to this site. So we have we've had up to 4 billion already invested over 30 years here. And as I will be talking about in a little bit, there are significant plans for further investment. So our research is broken down into 5 areas. We have cancer, aging, and somatic mutations. And so this is looking at patterns of mutations throughout the course of our life. So I think most people on this call will probably be familiar with the concepts of single mutations causing cancer. So the BRCA mutation is obviously the one that I think people know the most about. So a mutation in your BRCA gene, or particular mutations within your BRCA gene, are linked to breast cancer. But this is actually thinking about how mutations accumulate in our genomes over our lifetime, and how those may progress into cancer, or how you may end up with healthy aging. And so it's really about sort of tracking, almost doing archaeology to think about how those mutations have accumulated, what caused them, and then thinking about the impact that they've had on your body over your entire life history. Our next program is cellular genetics. The main project in this program is something called the Human Cell Atlas. This is a huge global initiative that is being co-led out of the Sanger Institute and the Broad Institute of Harvard and MIT in the US, but it is a grassroots initiative that has partners all over the world, and any research group, whether it's in an academic setting or in an industry setting, is free to join this initiative and contribute to it. And the purpose of this is to sequence every individual cell in the human body, and to really get a really fine, detailed map of how the body is built up. Currently, if you want to know what a cell type is, you would either look at it down the microscope, or you would take a bit of tissue, you'd mash it up, and you might sequence it and look at the gene expression, and the pattern of which genes are switched on and switched off would indicate which tissue it came from. But that's really an average of over all of those cells. And in addition, often what you see down the microscope doesn't align that well to the gene expression. So there's quite a lot of, it's actually quite difficult to identify what individual cells do. So this is really, the analogy that quite often gets used is Google Maps. So this is taking it almost down to the individual house level. So if you think of an organ as a city, we are getting down to the individual house and understanding how every single house builds to create a city. The next program is human genetics. This effectively has 2 areas of research. There is common disease. So this is thinking about complex genetics that cause common diseases like irritable bowel syndrome. And so while irritable bowel syndrome isn't often thought of as a genetic disease, there are genetics underlying it, but they're very complex. And so understanding how that causes diseases like irritable bowel syndrome is one area of research. And then the other is looking at rare disease, which is highlighted in the image here. So this is our Deciphering Developmental Disorders program. And I think, rare disease is something that many people, I think, are familiar with. It's often a single mutation causing a rare disease, developmental disorder. It's a slight oxymoron, but rare diseases are actually very common, and they have a significant health burden within the UK, and actually most countries have significant health burden from rare diseases. And so the DDD program has actually sought to diagnose children who had been on a diagnostic odyssey and had undiagnosed rare developmental disorders, and they sequenced 14,000 children in the end and their parents. And we've been able to provide diagnoses for a bit over 40% of those children, which may not sound that high, but is extraordinarily high because these children have been through the health system for many years and have been seeking a diagnosis. And we are continuing, as we continue the research, we go back and reanalyze people who don't have a diagnosis. So that number will continue to rise. Our Parasites and Microbes program is looking at infectious disease. So this is thinking about how diseases spread across countries and spread between humans, and also understanding host pathogen interactions. This is where our COVID sequencing emerged from. So we've been studying cholera and pandemics for many years. We also had been running proof of principle studies around things like MRSA spread in hospitals to show that you can use genomic sequencing to identify how or to track effectively who is spreading the virus to who, and you effectively trace it back to individuals and shut down the transmission there. And then our final program, which is it's our newest program and is a significant deviation from our historic work, is the Tree of Life program. So this is part of a global initiative called the Earth-wide Genome Project, which aims to sequence all the species of life on Earth and provide reference genomes for those. We are starting modestly with just the UK and Ireland. So I didn't know this before this project started, but the UK and Ireland is actually, despite being a relatively small landmass, is extremely biodiverse. So we actually have around 70,000 eukaryotic species. So these are species with nucleuses in their cells. And so the aim is to provide a reference genome for every single species, eukaryotic species in the UK. This is a significantly challenging problem. Reference genomes are much more difficult to make than once you have a reference genome, you effectively can use it to start scaling up sequencing. But doing the first one is always difficult, and preparing DNA from different species is also difficult. So this is going to be a big technological challenge for us. We also take on large-scale strategic projects. So we just completed the sequencing of UK Biobank on behalf of the government. So we did half of UK Biobank with a company in Iceland called Decode. So we did 250,000 human genomes over a 27-month period. And by contrast, the first human genome, which we were part of, took 13 years to sequence and took 7 organisations to do. So in the space of roughly 25 years, we have gone from 13 years for one genome and 7 organisations to 2 organisations doing 500,000 in 27 months. The other project, which I mentioned earlier, was our COVID sequencing. And so obviously, we were not doing this before the pandemic, but once the pandemic hit, we talked to Wellcome and we talked to the UK government, and we pivoted our sequencing fleet to start sequencing COVID genomes. And so for this, it was quite a logistical challenge, and also obviously, again, this was a new virus, and so there was quite a lot of preparatory work that had to be done. At the height of the pandemic, we were sequencing 64,000 COVID genomes a week. This did change during the pandemic, but at the start, what we were actually doing is we were bringing in all the sequencing plates from the Lighthouse laboratories. So people were turning up for testing, for their PCR testing. Their sample would go into a 96-well plate, and later 200 bigger plates anyway. And the PCR would come back whether it was positive or negative, and then the whole plate would be sent to Sanger along with all the other plates, and then we would cherry pick the positive samples and sequence them. And so this was a huge feat of robotics, first of all, just to get the positive samples out. As I said, we were doing this on behalf of the UK government. Some of you may have noticed the UK was very adept at spotting variants, much more so than other countries. It wasn't because we had more variants, it was because we set up this consortia with UK hospitals, UK universities, the Lighthouse laboratories, and did this sequencing. And so the UK was really a world leader in this, and actually I think has created a template for tackling infectious disease in future. The cost of this was around £26 per genome, which I think was a bargain for the taxpayer. It really did actually inform policy making. I think it actually was very effective in preventing some transmission. So we are continuing to sequence. We also, as I mentioned, we brought in all of these plates by the sort of end of the pandemic, if not that it's necessarily ended, but by the end of the pandemic, we actually had over 20 million samples sitting in a car park in refrigerated reefers. And our scientists have always, they're always thinking. And of course, everybody who turned up for testing at a Lighthouse laboratory was symptomatic. So they all were ill, but not necessarily with COVID. And so we're now going back and we're sequencing all of the negative for COVID samples to understand what respiratory illness in the UK looks like during a winter season. And we will be also monitoring the next winter to look at respiratory illness and how that transmits across the UK. We do work with industry, so this is probably our biggest industry partnership. This is called Open Targets, and it is a pre-competitive collaboration with our partner, Embl EBI, who is the other research institute on campus. And then we work with pharmaceutical companies, and this is open to any pharmaceutical company. And we've actually had a bit of a rotation of different partners. Currently, we have Bristol Myers Squibb, GSK, Pfizer, and Sanofi. And the scientific basis for this collaboration is that drug discovery is incredibly expensive because of the high failure rate. However, when identifying drug targets, if there is genomic evidence to support that drug, the validity of that drug target, it is more likely to make it to market. And that is basically the principle behind this. So the idea is to use genomic information to better identify potential drug targets and hopefully eventually get those through to market. And I do have a couple of slides from that platform. So all of the data on that from that collaboration is openly available. Anybody can go to the website and look at this information, and effectively you can go in, identify the disease that you're looking at. You can see what genes are potentially implicated, and then you can click through on those genes and see what the evidence is to support the involvement of those genes. And that is available to, despite it being a public-private partnership, that information is made available to everybody, and it's made rapidly available. I will just quickly talk about the amount of data we produce and the kind. So we have, as you can see from this graph, we have been increasing the amount of data we produce exponentially. The different colors represent the introduction of new sequencing technologies. So the pink on the top is the introduction of our NovaSeq, and you can see that prompted a massive increase in the amount of data production.
Sarion, the writing of the, I think it's years at the bottom is very tiny.
I know, I do apologise.
So pull that out?
Yes, so on the far right, we have 2022 going back to 2017. So you can see that you can actually see in 2020, I'm not sure if you can see the math, you can't, but there's actually a plateau in 2020 where the pandemic hit and we temporarily stopped sequencing. And then you can see that we did not slow down after that, that despite most of us being at home, our sequencing teams were in and producing data. So we're up to about 47, coming up to 50 petabytes of data. This is a huge amount of data. We have our own data center, which is now rapidly running out of space. So we are looking at having to build a second data center shortly. So data production and data storage is always a bit of an issue for us. I did pull out a few different numbers. In July, we sequenced apparently only 17 different species, which normally I'd say we do significantly more than that. We produced the equivalent of 80,000 human genomes in 1 month. And I'm not even going to attempt to say how many DNA bases that is, but you can see that we are producing significant, very large numbers. And last year, we really started to ramp up the number of sequences, the number of species we were sequencing. So we were up to about 3,500 last year. The majority of these were pathogens, but we are beginning to bring it with Tree of Life. We are beginning to bring in other species in there. The most commonly sequenced though is human. So that is the thing that we sequence the most of. Obviously we had UK Biobank, so there was 250,000 human genomes in there, but we also have all of our cancer projects and Human Cell Atlas projects as well. So a lot of information on humans being gathered there. And again, I apologize for the small numbers. This is because Tableau did not want to play ball with me, but we are rapidly increasing the number of species that we are sequencing. This is a huge challenge for us. Sequencing a new species means creating a new protocol for each species and understanding and figuring out how to create a library prep that goes onto the machine, and then having to assemble a reference genome for those. So in the graph on the left, basically this is the amount of sequence data for different species that we've been producing. On the right is the numbers. So you can see that in the bottom of that graph on the right is with 2023, the bar above it is 2022. So we're halfway through 2023, and you can see that we've almost produced the same number of species that we did in 2022. And so we are really beginning to hit the exponential phase of this project, and we will be increasing the number of species quite rapidly. We are an open access institute, so all of our data is made available to researchers and interested parties. So this is actually Mike Stratton, our recently former director, who stepped down as part of a campaign to ensure that data remained available as GDPR was going through the European Parliament a few years ago. So all of our data almost all of it goes to two repositories. So animal and pathogen data goes to the European Nucleotide Archive, with the exception of the COVID data, which goes to a database called GISAID. This is completely available. Anybody can go and download it. It's there, and it's rapidly released after it comes off our pipelines. Human data obviously has more sensitivities around it. So we have a managed access process that places terms and conditions on the use of that data. And so there's a contract that's required to be signed, but it is a standard agreement for everybody. It's not negotiated. So again, anybody can apply to access it. We won't always grant access, but for the most part, we do. And this is because we don't monitor our non-human data. This is just looking at the human data. So since 2015, we've signed nearly 2,000 data access agreements. Most of these data access agreements have multiple data sets within them. We are sharing around the world, particularly, unsurprisingly, with Europe, with North America, Australia. We're seeing an increase in interest from China and India. We are slowly seeing an increase from the African continent, particularly South Africa, and also from Central and Southern America. But we are really interested in increasing these numbers and improving that uptake of data. We have done a bit of research as to why we have such low numbers, and there's a number of issues, and it's quite a difficult, knotty problem. But I'm hoping that over the next few years, we will start to see more data being accessed from those countries. I just wanted to quickly mention a few of the projects going on within my own team. So we are the policy team. I have 4 people in my team at the moment: Hayley, David, Mate, and Gemma. This is a snapshot of the website, which is quite biased because I think, like most people, we're not very good at updating the website, and it tends to only be the things that we suddenly need to get a statement out about. So the team does a huge amount of work on things like immigration, GDPR, data protection, all of those kind of things. We've also done a lot of work with Horizon as well, and we were delighted the week before last to finally re-enter Horizon Europe. But we also do work on things like representative research. So we're trying to develop a strategy to ensure that our research is more representative of the communities and regions that we're studying. We are looking at equity in our research and how we can ensure that we're embedding equity into our partnerships, and that particularly with lower middle income partners, so that they are benefiting and that there aren't power disparities there. And then we're also looking at things like open science and at the bioethics, and so thinking about things like synthetic genomes, creating artificial genomes, and what the ethics of that might be. I'm going to quickly wrap up with just a quick kind of overview of the campus itself that we sit on. So this is the Wellcome Genome campus, picture taken from the sky. Sanger actually occupies 4 buildings on campus. I'm currently sitting in the buildings towards the top of the picture, but we have a sequencing fleet down on the far right hand side. We then have 2 buildings with laboratories, offices, and our data center, which is the glass cube. And we have what the sort of building with the brown roof is our storage, our stores and logistical services building. We share the site with the European Molecular Biology Laboratory and EBI, so EBI, so this is the European Bioinformatics Institute, and they effectively are, they handle all of our data for us. So we produce it, we obviously do analysis ourselves and research, but they then archive it, curate it, and serve it up to the worldwide community, along with providing data resources for Europe. And so lots of scientists and research programs use their services to ensure that their data is available to the research community. Having them on site has been really important for us. They're probably they are definitely our most important collaborator, and I think we are very open in our work with them. We also have a unit called Wellcome Connecting Science, which is part of Sanger, but sits slightly separately. So they provide the training and public engagement. So they're our scientific outreach. There's courses and conferences. So they provide training for the community on genomic sciences, from everything from genetic counselling. We recently ran a course on genomics for midwifery, all the way through to teaching pathogen genomics to different groups. We also run courses in low-income countries to build capacity there and do train the trainer type events to ensure that knowledge continues. We have a incubator space for small and medium enterprises called the Biodata Innovation Centre, which has some of the spin-outs from Sanger and from EBI, but also startups working in genomes and biodata. We also have a few companies in there who are multinational companies with large headquarters but want a small office on site, because that co-localization with that genomic capacity is incredibly important for many organizations. And then the reason why I'm really presenting this is that we have planning permission to expand the campus. And so we will be expanding the campus approximately threefold. This will be run by Wellcome, and they are investing a significant sum of money into doing this. They recently bought a development company called Urban and Civic to run this project. And there will be research organizations, commercial space, homes, and community services there as well. And we're really excited about this, because I think this campus is already of national and international significance. It makes the UK a world leader in genomics, but this expansion, I think, will really cement that. I very quickly was just going to mention a side project that I've been working on, which was the European Health Data Space, which some of you may have heard of, which is a European initiative to both support individuals having access to their health data and being able to move their health records around. But I think of more interest, at least for Sanger, is around the secondary use of data for research and ensuring that there are mechanisms that allow data sharing. I don't love this picture, but this is the one that the European Commission has been using. So effectively, they aim to set up infrastructure that allows countries to monitor access and to effectively allow researchers to access health data within those countries, do analysis. It's a federated structure, so ideally data won't be moving across boundaries, and you'll be taking your analysis to the data rather than the other way around. Because Sanger and NHS Confederation have been involved in the programme to set this up, we are hoping that the UK will be able to participate in the European Health Data Space when it is set up. And so I'm sort of giving it a plug to everybody and anybody who can listen to really talk about the importance of this programme and to ensure that the UK can benefit really from having access to these data resources. And I'm going to end it there and say thank you very much for listening, and thank you for inviting me. I'm happy to answer any questions.
Well, thank you, Sarion. I told you it was going to be good, didn't I? I told you it was going to be good. Goodness me. I mean, it just brings it all back to me. I was lucky enough to get a tour around the facility. with Sarion, as I say, earlier this year, and for a humble guy like me who knew nothing about it, I was just completely blown away by the scale of what you're doing there. There's a super question from Ruth that you may have seen or not in the chat as you were going along. Ruth says, the question is, what does this mean for the future of health services, given the speed of innovation we've seen through COVID and move towards collaboration? I'm going to give you the opportunity to answer that. So what's your view?
So, I mean, I think it's a challenging question. I think there's always the question about upfront costs with this. I think we have been able to demonstrate that there are massive scales of economy here, and the UK, with its centralised healthcare services, is able to implement this in ways that other countries aren't able to. And I do think ultimately having genomic information does support better decision making and better healthcare. So effective, I think it is a cost-effective technology for the NHS and for any healthcare system. However, it does present some challenges. So historically, the NHS has a genetics service, and you have geneticists and train. You have people who train in genetics, and that is a specialism in itself. Genomics cuts across all of those things, so everybody needs to have a genomics education in order to be able to engage with their patients on this. And so I think training is a huge issue around this, but I think there are a lot of things that can, that we will start to see genomics really benefiting patients. We're already seeing genomics being used routinely in cancer, developmental disorders, and I think we're just going to keep seeing it happening. And then obviously with COVID, we now are seeing the UK government is really thinking about genomic surveillance for pandemic diseases. We're working with low and middle country governments to support them developing these systems and services within their own country as well. So I think it's going to be gradual, but we're going to see it happening. So,
Ruth says you probably see what she's written. Absolutely agree. We're not good at stopping the old. You're right, Ruth. You're right. Yeah. But I think what you'll, if you are lucky enough to have a tour of the Institute, I mean, what strikes you is the acceleration that Sarion referred to earlier. Whereas, when they started, it took, you forgive me for not getting the maths on, it's absolutely right, Sarion, but when you did the first genome, it took you 13 years, I think that's right. And heaven knows how many different contributors. Yeah. Now, not so long later, you're doing 250,000 of these things, in the same time it takes you to blow your nose, as far as I know. So it's that acceleration that I think is most telling. And one can imagine what that will mean for the future of things like pharmaceutical development, specific, individual human treatment for specific disease as we go along. Yeah. Where you'll not be given something that might work, you'll be given something that they know will work. And I think that's probably even going to be within my lifetime, which would be extraordinary,
Absolutely. I mean, there's a big discussion around newborn sequencing at the moment. So the idea that every child would have their genome sequenced, and it would be on record and accessible to any clinician who needs to access it. There's obviously a number of ethical challenges around that, and I think that's very much, it's not something that I'm involved in, but it is hugely, I think it will happen, and we will see that kind of information being part of the health record in future. So
there you go. Oh, hey, Ruth's going to launch a new cancer service at CUH. Oh, good for you, Ruth. That's good news. That's fantastic. You must get, you and Sarion must get in touch. You need to pop along and have a look at it, Ruth. It will blow your mind, I promise you. The other thing, I was in Iceland earlier this year, Sarion. I went fishing there, but one can't help driving out of the airport there than to see these. They just look like warehouses, but of course what they are is they're data banks. Yeah. Using the cheap power that Iceland has naturally coming out the ground, because this is a very energy intensive business
It's the cheap electricity and cold temperatures, because they need the cooling is what actually uses all the electricity up. So if you see our data center, it effectively is 1 story high, and then we have what looks like a big glass block sitting on top of it, which is 2 stories high, which is the cooling. So so Iceland is quite good for data centers.
But it's going to be exactly. But it's going to be interesting as you develop and as you accelerate even more the activity that you undertake, particularly with your new space that you're going to develop. You know, the energy bit and how you do keep everything cool, and where the heck do you put all of this data? And you know, it's
the energy crisis has hit us quite hard. We have a very large electricity bill, so
more activity in Iceland, perhaps.
Yes. So I mean, it's I think vaguely related to that. I mean, EBI, the other institute on campus, just to give an idea of the scale of the kind of data flows that are in there. One of their fun facts that they like to give is that on any given day, the BBC is usually the biggest data exporter in the UK. So this is sending data out of the UK. But every now and again, EBI pips them. So every now and again, EBI is the biggest data exporter in the UK, sending data out. And so that is a significant amount of data that is being transferred out of the UK at any single moment. So it's, keeping that pipeline going is hard work.
And is there any global conglomeration of what you're all doing? I mean, I appreciate we're very heavily bound to you, and thank goodness for the Horizon News, you know.
Yes.
So
a lot of our projects are,
at least it has, you know. What about globally? Do countries tend to get together, or is it more?
Yes, maybe not countries in terms of governments, although governments do. There are a lot of increasingly national initiatives around genomics, and they do tend to collaborate with each other and especially share learnings. But we certainly work in international initiatives. We do tend to often lead them, but not always. So I'm quite involved in an initiative called the Global Alliance for Genomics and Health, which is around creating data standards and policy standards for genomics and health data. So this is to try and ensure that data that's being produced by one country, that researchers around the world can use it, because interoperability is always a huge problem with any data project. So this is about trying to ensure that we're all effectively talking the same language and using the same standards. And so that's one initiative that we're involved in, but we're involved in the International Cancer Genome Consortium, which has produced, I'm sure Ruth knows about, probably knows more than I do about it, in fact. But yeah, so we're involved, we've been quite heavily involved in that. The Human Cell Atlas is a global initiative as well. So there are a lot of global initiatives. Scientists generally tend to collaborate even when their governments aren't necessarily playing ball with each other. So we have continued to work with organisations around the world on this.
It's very impressive. Let me open it up. Does anybody else like to ask Sarion a question directly? You know, you're not going to get the opportunity for this very often in your lives, folks. So, you know, this is one of the more higher echelon kind of scientists that I've ever had the privilege of meeting. If anybody would like to ask a question, just unmute and go ahead. I can only assume that people are struck dumb, Sarion, by the extraordinary brilliance of what you guys are doing there. Well, okay, look, you've had your chance. Don't say you didn't have your chance now. You had your chance. In that case, Sarion, I'm just going to let you go. I think that's just been fantastic. I'm so grateful to you for coming on and explaining the work of what you do at the Wellcome Sanger Institute. Isn't it fantastic that Wellcome have been able to put so much money in over so many years to support the brilliant work that you're doing? And the extraordinary thing for me is most people in this country haven't the first idea that this is going on. No. They have the first idea that behind all of the advances in treatment for goodness knows what it might be that they're seeing, you can bet that one of the catalysts working quietly in the background is you and your colleagues in Cambridge. So thank you. Thank you.
I mean, on that, I would say that I think in the pandemic, the UK actually showed how brilliant It really was. So it wasn't just the sequencing, although obviously I'm very proud of that, but the vaccines and also the clinical trials were, hugely powerful. And so I think UK science is great, but we do need to continue supporting it. So on that stump pitch,
Sue says she's just struck dumb, as I said. So there you go. You've done good things today, Sarion. You can sleep soundly tonight, knowing that members of the Institute of Health and Social Care Management now know more about genome sequencing and the work of your fabulous Wellcome Sanger Institute. So thank you very much indeed. We really appreciate it. And good luck, Ruth. Get over there. Go and have a look.
Yeah, absolutely.
Lovely. Thanks, Sarion. Bye-bye. Bye-bye all.